Well, in previous lecture, I was talking about training and inference. So I explained all the things that you need for conditional random field. But for historical purposes, I want to explain this article from 2001. So about 22 years ago. But it is very important because you should know the historical process that these ideas are developed. And because, for example, next lecture I want to talk about BiLSTM CRF. So you should ask me why this is going in this process and evolving in this way. So CRF is a discriminative model, and the probability of your latent variable given your observation x is equal to this log likelihood, and we normalize it with this normalization constant, also called partition function in physics. And so theta is the global weights vector, and the denominator sums over all possible output assignments. And you see it is undirected graph. CRF is an undirected graph, but HMM is a directed graph. So there is no direction from observation to state and or between the states. So the probability of a transition between labels may depend not only on the current observation, but also on the past and future observations. In contrast, generative models like that HMM must take every strict independence assumptions on the observations. For instance, conditional independence given the labels to achieve tractability. So this is the definition. For example, we have a graph, we have vertices and edges, and so y is the index by vertices of G. And so x and y, these CRF, x and y is a conditional random field in case when condition on x, the random variable obey the Markov property. So it doesn't, so if it is the neighbor or not, it doesn't matter. The probability is the same. So the probability of your y, you see, this is y, this is the states and the observation. So we have an label sequence y given your utterance x. For example, if you're working on NLP, x could be an utterance. Or if you are a roboticist, the pictures that robot is taken with the camera is the observation. So the probability of y given x is this. So what we are going to learn are these parameters, lambda k and mu k. And so lambda k, if you compare it with those things in hidden Markov model, if you want to compare that, you can say that lambda k could be seen as transition and mu k is the emission. And related to emission. So these models, and you know, fk and gk are, we assume that they are given and they're fixed. For example, g could be a Boolean, but you see in the next lecture, we are not talking about Boolean features anymore. They're hard to compute. They could be 1,000. They could be lots of, and either the sparsity, we will get into sparsity if you want to talk about these traditional approaches. So nowadays we use a different approach, not just Boolean features. So our loss function is convex. That is really good news. This log function, you see, it's linear combination of some functions, and so we depending on the number of features. So we sum not only on the number of features k, but also overall edges, because you have lots of these edges. And here we have observing that. So, for example, k is the number of features, and for example, E1, E2, E3, E4, these are edges that you need to for transition. And we have vertices, these, for example, vertices, this, when you are here, this is a vertex, second vertex, third vertex, fourth and fifth vertex. And you see these are just Boolean things. And so, as I said, the corresponding parameters, lambda and mu, play a similar role to probability of transition and probability of emission. But CRF is much more expressive. It's like neural network, very expressive. That's why people in machine learning used to work with CRF. Even in 2023, we combine it with different architecture, CNN, BiLSTM, BiGRU, Stack LSTM. We combine it with CRF because they are very expressive. But HMM, it's very nice, it's very beautiful. Of course, both of CRF and HMM use dynamic programming, but CRF is more expressive. It's like, you see, you have something and you get the output. It's like a neural network. So the left is the HMM, the center. I have a playlist for this maximum entropy Markov model. And this is our CRF that we are talking about. It is not directed graph, and it's very expressive. So we write those things like this because it's cleaner. So the author created this variable, say that this is e to the something, but that something is lambda k, the features of k, because these are transitions, and mu k, gk. So f and g are your features. So lambda corresponds to, if you want to compare it, it's like transition parameter. Mu k is the emission parameter. So because the authors are very creative, with that mi variable, you can create it very beautifully with very less mathematical terms. Just a multiplication of mi, because they are independent. You have different observation, different times, and you sum mix. It's a marginalization of the denominator. So you see very compact representation, very beautiful terminology. And of course, you should note that just like biology, just like recurrent neural network, here we have y start and stop to denote that what is the start and what is the stop. We don't need to continue anymore. So just like previous lecture, these are again the same thing. We want this to be equal to, so e tilde g, we want it to be very close to that, so that this one goes to 1 and log of 1 is 0, so delta mu k converges to 0, so mu k is converged to something. The same thing for lambda k. These are the same thing, but with a different terminology. For example, he introduced that slack variable, slack features, And here T is the total feature count, because these are because they are binary Boolean, and so Boolean is like counting, because it's just one, maximum one, and otherwise it's zero, each of these. So T is becomes the meaning of T intuitively. It becomes the total feature count. So here S is large, so that's why it takes time to converge. It may converge very slowly, taking very small step toward the maximum. And the algorithm T is the maximum of T of X and Y. So these are variables just as we defined in the previous lecture. They are the same thing. But for historical purposes, it is interesting to also review this article. And you see the power of space tagging experiment. For HMM, the error is 5%. For CRF is less than that, but it's almost the same. But this maximum entropy Markov model is 6%. You know, this had label issue, label bias issue.